SwayamPrabha. Digital India. Educated India.
Welcome to today's lecture. So far we have been discussing about the geostatistical method for estimation of the quality parameter in ore bodies, and we have got a brief idea about the nature of the variability of this particular variable, which we are considering as a regionalized variable behaving in intermediate between random and deterministic, and the behavior can be quantified with respect to the spatial domain, spatial influence of the variability of the data in the form of the semivariance, where we saw the nature of the semivariance and the different types of models, that mathematical models that could be fit to the semivariance in terms of a spherical model, parabolic, exponential, linear, and so on. And before we and also we just made an introduction. So this exercise of the variogram modeling, at least in this particular context, is it forms the background for the estimation procedure, which is basically known as Kriging. Here we go for the estimation of the regionalized variable at any unknown location and go ahead with the calculation procedure. We will just see briefly how the calculation goes on. Let me tell you at the beginning that this procedure that I am briefing here, elaborate, giving the bit of an idea or introducing this subject to you, actually it's pretty much elaborate, and it involves quite a lot of exercise as far as the modeling of the variogram is concerned, because we have to take into account many of the situations such as the anisotropy. For example, when the semivariance, nature of the semivariance is different in different directions, for example in the north. So whenever we see spatial data, we always put them in the form it is north, south, and east, west. So we always represent in the form of whenever we have any particular point in space, we express the spatial data in terms of easting and northing. And when we discussed the data in the form of grid, the x and y direction, so we know that the semivariance could be different in different directions, and that is one of the reasons, and we have to have the methodology to have something like a average semivariogram, or to have the model in spite of this kind of anisotropy. There could be missing data, there could be outliers. Outliers are the ones where we can have in an array of points, which are basically represented on these nodes, we might get a situation where a particular value certain value becomes unusually very high or very low compared to the values in the surrounding. In such kind of situation, we call them as outliers. So there are many elaborate methods which are there to take care of these situations like anisotropy, missing data, outliers. So what is being presented here is an overall idea that one can have to deal with the spatial data and do the calculations at this particular level to have an idea as to how a quality parameter for an ore body can be estimated once the nature of variation of the quality parameter like grade is known in a data matrix. So before we go to the procedure, just that I'll be discussing about the Kriging process. It would be worthwhile just to note that there are many commercial softwares which are available for processing of such kind of spatial data, the real live data like data that is acquired from any ore body or otherwise any kind of a spatial data like depth of water table, surface elevation. All these type of data we defined in the beginning as regionalized variable. So there are many commercial softwares which are available, but there are to my knowledge there is one teaching software that is available to do geostatistics, that is the practical geostatistics. This is mostly available as a group of programs which are available from the site by two scientists, Isabel and Clark, from their practical geostatistics web page, where these programs can be obtained, and there are numerous set of data, small and big data sets, which data set could be observed. For example, the data set could be having in terms of easting, northing, and any attribute value that we could talk about in terms of the value of the metals or one or more than one metal grade which will be given at different points, and such kind of example data set can be taken, and this exercise one can always get a feel of plotting these semi-variograms and also to fit them into different type of model and also go on with further exercise. So now coming to the estimation procedure, which is known as Kriging by the famous the person who pioneered this exercise, Kreis. So let's look at what this exercise could be for estimation of the regionalized variable at any unknown point. Let's first consider this is the spatial domain in which the semi-variogram is valid, the model, whichever model has been obtained by doing the exercise. And first let's assume that the data or this particular procedure that we are discussing right now is on stationary regionalized variable, and such a Kriging exercise which is done on stationary regionalized variable, once the semivariance is known, the model is fit. We will first look at the method which is known by the name as point Kriging or punctual Kriging. Essentially telling us that the value of the regionalized variable at any particular point can be determined by using this procedure. Let's think that we want to estimate an unknown point where P the value of the regionalized variable. Let's say it's our grade, where we want to and this is the special limit within which the semi-variogram model is valid. And now if we do that, then we have to do it with respect to the some points, some known points on which the value of the regionalized variable is known. So if we have to do that, so if we have to suppose the value of the regionalized variable at y is denoted as yp. So this yp can be estimated based on some known points. So how many known points we could possibly have? So our common sense will tell that, okay, in order to have any kind of an estimate for an unknown point, we should have minimum 3 points in the neighborhood where we should have the value known from which we will be able to calculate. And here, so the first thing that is available to us is a variogram, is a semi-variogram. Model with the range or neighborhood known. Let's take it for the time being that it's a linear model where gamma h is equal to alpha h, where alpha is a constant quantity and this is h, and here is the range is defined. So if you are to do that, so then if we want to have 3 points, let's take 3 points, point 1, point 2 and point 3, and the coordinates of this in the easting and northing are known. Let's say this is the origin. So the coordinates of point 1, point 2 and point 3 are all known to us, as well as point P. So we will use a simple formula for calculation of this particular variable at P as sigma I equals to 1 to 3. We can put n is equal to 3, 1 to 3, wi and yi. That means it will be y1 w1 plus w2 y2 plus w3 y3, and these w's are the wi are the weights. And then we please remember the inverse distance weighting method we used. It's a method which we are using here is more or less analogous to that, and here the constant is that sigma wi will be equal to 1. Now how we can do that? So here the value of the regionalized variable at P is unknown, and the value at 1, 2 and 3 are known, and the only thing that we have here is the semivariance, the model semivariogram. So if we, so here we can, so W1, W2, W3 are the unknowns which we have to solve. So if we have to solve, then we have to have 3 equations. So let's try to formulate it. So these 3 equations, when we formulate, we take help of the semivariance. So here it is gamma h11 into W1 plus gamma h12 W2 plus gamma h13 W3 will be equal to gamma h1p. Here it's very well understood. Gamma h11 is the semivariance of 1 with respect to 1 itself, 1 with respect to 2, 1 with respect to 3, and these values are all can be calculated once we have the gamma h as a function of distance, because we know the distance between the point 1 and 2, 1 and 3 and 2 and 3 respectively. So here again gamma h 21 W1 plus gamma h 22 W2 plus gamma h 2 3 W3 is equal to gamma h 2p P. But we know that we have another equation here where W1 plus W2 plus W3 is equal to 1. So what we have, so this is an overdetermined system. So what we have to do, we have to get a unique solution for a situation where there is the number of equations are more than the number of unknowns. We will introduce a slack variable as lambda, and we will put here as lambda plus lambda, so that now our number of unknowns are 4 and the number of equations are 4. So if we now put this in the form of a matrix. So here we put it in this way. So here are the this is the way in which you can write it in the matrix form. This is gamma h1p, gamma h2p, gamma h3p, and this is 1. The last equation w1 plus w2 plus w3 is equal to 1, and all these. So here the as it can be seen here that this is the matrix A, and this is the matrix X which we are going to solve, and this is the matrix P. Now you could the interesting thing which you would observe here is that this matrix has these diagonal elements. If we are in this case we are considering a stationary regionalized variable, and we take that there is no nugget effect. So if there is no nugget effect, then the gamma h11, gamma h22, gamma h33 are 0. So we will have this diagonal element as all zeros, and this is the form of the matrix that we could write. So we can use our simple knowledge of matrix algebra, and we can solve this. And in case there is a nugget effect, this nugget effect is known, and this diagonal element will all have the same value, and we can solve this. So if this forms a x is equal to b, so x would be A inverse b, because this will be 3:3 and this is 3:1, so it will be 3:1. So we will get the column vector which is our x, so which will be the value of w1, w2 and w3. can be solved in this way. We can we will be posting a few example exercise with this kind of data, taking some real data, synthetic data from any data set, and so finally we will be able to get our value of the regionalized variable calculated at a point P as W1 Y1 plus W2 Y2 plus W3 Y3. And as we have said before, these values that we get here will essentially be a value on which the true value for the regionalized variable at point P is actually not known. In spite of that, we still could possibly approximate what kind of error we might have introduced in this calculation, so that we know that it could be calculated. If I represented a sigma z square as W1 gamma h 1p plus W2 gamma h 2p plus W3 gamma h 3p plus lambda. So this is the kind of error, the standard error of estimate, which by taking the square root of it, which we can calculate. So this particular exercise is the punctual Kriging or the point Kriging. As we discussed before, we sometimes in terms of our selective mining unit of the block, which we have discussed before, if this is the body that we divide it into different blocks, and we need to report an average grade for a particular block. Although we know that as an ore deposit we come up with a value which is the average grade for the ore deposit with uncertainty, and sometimes with reporting the cutoff grade. But for the mining operations, for the continuous mining operations, and to know exactly the quality parameter, because this ore body is actually mined discretely in the form of the selective mining unit of block. So the kind of Kriging estimate which is essentially required for this is known as block Kriging. But this block Kriging is actually nothing very different from the method. Also here we would again go by our assumption of stationary regionalized variable. The grade is behaving like a stationary and behaving in a stationary manner, and in that case, suppose now we need to have a block of this size whose average grade has to be determined, and this in the context of the larger the ore body that we have. Maybe that we just need to have the central point here for the estimate of the block average. So this could be also be done in a similar way. Taking this number, one of the ways that it could be done is that this particular point will be just be treated as the similar way in which we have treated the previous example as estimating the unknown at any particular point. So in this case, the block center point of the block becomes the point at which we want to do the Kriging. There also we can do the same way by taking some points in the close neighborhood, and can do the if the spatial influence is not violated, and we can take points anywhere either within the block itself or just a little outside, taking some points, we can still calculate the point, and this kind of formulation of the matrix that we have shown here will be exactly the same way that it could proceed and could assign a particular value as the average for this particular block. Alternatively, we can also do, and in that case our matrix method will be exactly the same that we have seen here, or we could possibly take some 4 unknown points, within the block itself and estimate the value for this grade at all those 4 unknown points, and then take a point average of those 4 and assign it to the central point. In this case, it can be done individually for this point 1, 2, 3 or 4, or it could be done even together by using the same kind of a matrix. Just one point to recapitulate here, that if we could see that when our number of unknowns were 3, W1, W2 and W3, and we introduced one slack variable, and the size of the matrix becomes number of unknowns plus 1, 4 cross 4 matrix. So in this case, if we can use the same 4 cross 4 matrix for this individually these 4 points, or can do them simultaneously by taking another 3 points here and in the outside in the region in the closed spatial inference, and can solve a 8 cross 8 matrix to solve for the weights for each of these 4 unknown points and get an average which will be applicable for the central point for this block. So block Kriging is essentially nothing very different from the normal point Kriging methods. See, other kind of Kriging which is sometimes used and is used in mining industries often is the indicator Kriging. Without getting much into details of that, I can just briefly explain. Suppose this is the spatial domain in which the semi-variogram is fit, and then we are trying to actually do the geostatistical exercise. There could be many points within this, and now each point here is assigned with a value of the grade of some finite value. Let's say any finite value, this is 0.5, 1.2, 0.8, 0.7, 0.6, 0.3, 0.2, 0.1, something like that. And now suppose we in this particular deposit, from the calculations that we did earlier for the calculation of the cutoff grade, let's say that we find we have come out with the cutoff grade of 0.3 weight percent of the metal. So here, out of these points, the points which will be above 0.3 can be marked as 1. For example, in this example which we have seen here, say this will be pointed as 1, this will be as 1, this will be as 1, this will be as 0, this will be as again 1, this will be as 1, and this would be as 0, and this should be as also 0. So that means the points where the grade is greater than cutoff is taken as 1, and where it is less than cutoff, is less than cutoff, it is 0, and greater than cutoff is 1. So now here it almost boils down to the situation that if we want to do the Kriging operation for any particular unknown point P here, then we would only be asking the question to ourselves that whether the grade here would be above the cutoff or below the cutoff. So that means almost it will be something like a finding out the probability for the grade to be greater than cutoff or less than cutoff. So we will be doing the Kriging taking the value as 1 or 0, this kind of binary number, and the value that will come out for this particular unknown point P will not be exactly the value of the grade, but in terms of the probability of the point having greater than cutoff or the less than cutoff. So with this, I would just conclude with this ordinary kind of Kriging methods, and in a very simplistic way and within the limits of this particular lecture series. So we'll continue the next class. Thank you.